didn't record already. So we were talking about the bone strength, and I am in the slide number 7. So slide number 7. This is chapter 8. We are still in chapter 8. So what is the bone strength? So bone strength is, so you have a bone like this, C and S. So C and S are bonding together. So this bone has some strength, right? So we need to supply some energy to break it. So how much energy we supply to break that bone is called bone strength. Make sense? Good. So let's say you have let's talk about this one. So you have this molecule CH. So this molecule is methane. So this is a methane gas. So if you put, let's say this is a vessel. So this is a vessel, and you put here 6.6 is a 1 mole is a 6.023 10 to the power 23 this molecule CS4. Yeah. So CS4, this is a CS4 molecule. So you put 6.023 10 to the power 23 molecules here in this vessel, and you supply energy here. So you supply heat. So you supply heat or electricity to this system. And how much energy it takes to break all these CS bond of this molecule is 1660. So you need to supply 1660 kilojoule of energy. So how many atoms, how many molecules are there? There are 6.023 10 to the power 23 molecule of CS4. So if you want to break all these bonds like this and make C and H like this, 1, 2, 3, 4 H and C like separate. So you need to supply 1660 kilojoule of heat. And since you are supplying that much energy from outside, we give the plus sign. Why we give the plus sign? Because it is endothermic reaction. We are giving the energy from outside, right? Either we are supplying the electricity to break those bonds, or we are supplying heat to break those bonds. Make sense? So that much heat energy we need to supply to break all these bonds, or from the 6.023 10 to the power 23 molecules of CS4. Now, how much is the CS bond strength then? So how many bonds we break here? 1, 2, 3, 4. To break 4 bonds, we need 1660 kilojoule, right? Now, how much is energy is needed to break 1 bond? That is 1660 kilojoule divided by 4. That is 450 kilojoule to break 1 mole of CS bond. Make sense? So if you are breaking all 4 bonds from the CS4 of that many molecules, you need 1660 kilojoule. But if you are just talking about only 1 bond, just this bond in the CS4, we need to supply 415 kilojoule per mole. Make sense? So that's how it works. So if you have to supply the energy from outside to break those bonds, we give the plus sign. Yeah, and we represent that as delta H. Delta H is equals to 415 kilojoule per mole. Why? Because we supply energy from outside to break those bonds. Because it's endothermic. Yeah, it's just like lab number 11 we did there in the lab. Suppose you need to make a bond. So we are just breaking the bond. So we give the plus sign here. Now let's break the bond. Let's make the bond. So if you want to make this bond, let's say you have C and you have H. You have C and H. So you have, let's say, you want to make 6.023 10 to the power 23 CS bond, right? 1 mole. 1 mole means 6.023 10 to the power 23 particle, right? So you want to make that many bonds here. So previously we were breaking this. Now we want to make it. So we bring the carbon and we bring the hydrogen and we put them together and we want to make the bond, right? So bond making process is negative. So if there is a C, there is a H. So if these two come together and form the bond, that is 415 kilojoule, and we give the negative sign here. Why? Because they form themselves and release the energy. just the opposite. Yeah. So when we are breaking the bond, CS, we give the plus sign. If the C and S coming together and making the bond, they give out the energy, and that we give the negative sign. Then the amount is exactly the same. Make sense? So this is 415 kilojoule of heat energy they release, meaning that, so if you put enough C and enough H here and convert, you just close it and they react together and they give out the energy while they are forming this bond. And if you touch this or you put the thermometer here, it's the temperature rises. So it's a kind of exothermic process. It's just like how you did it in thermochemistry lab in coffee cup calorimeter. Yeah, so that's how it works. Good. So let's do another one here. There are a couple of problems we need to do, and I told you to break the double bond, it takes very high amount of energy. For example, so if you want to break just one bond, you need to give 436 kilojoule of energy to break this one. But if you want to do break the CC bond, the single bond, you need to give 346 kilojoule of energy. If you want to break C double bond C, this bond here, you need to give 602 kilojoule of energy. Now, if you want to break this triple bond here, you need to give 835 kilojoule of energy. So if the number of bonds are bigger, we need to supply more amount of energy so that the bond breaks. It is very simple, right? It's just like there are, let's say, two ball here, let's say two ball here, and you are just binding these two ball with one string. It's easy to break this string and separate these two balls, right? Now, if you are binding these two atoms with the two balls with the two string, it takes large amount of effort to or force to break this bond. If you are making or binding these two balls together with the three string, more force to break those three balls, right? It's pretty simple. Yeah. So now we have an example here. So let's do that example. So now I am in the slide number 11. So we will use the slide number 10 in slide number 11. We have a problem here. So let's do that problem. So using the bond enthalpy, calculate enthalpy for the reaction. ENTHAL, enthalpy of a reaction. So what is the enthalpy of a reaction? So we exactly as a lab number 11, where you put a coffee cup calorimeter here, and then you put a thermometer here, and you put whatever the is here, and this is open a little bit here, and how much energy is released, that amount of energy is released or absorbed is called enthalpy of the reaction, right? So that's the enthalpy of reaction. If you do in the open system, like where there is a hole or something like that, so that amount of heat we call is the enthalpy of the reaction. So we can calculate the enthalpy of reaction without doing experiment. So if you remember the lab number 11, where we were doing the coffee cup calorimeter, we used the Hess law and calculated the amount of heat that may release by reacting magnesium with the water, right? Using the magnesium, we were doing something like this, magnesium and HCl. We did one time, in another time we did MgO and HCl, and then we had one heat here, 436, something like that. Here 100, maybe 137 like that. MgO and HCl, when we were doing that, we got 437, something like that, and we just rearranged this one, and we did like this. Mg plus H2O would give you around minus 313 kilojoule per mole. If you remember your coffee cup calorimeter, we are doing exactly the same thing here. Yeah. So let's say here is a reaction. We have a reaction. The reaction is like this: CH3, so CH3, C double bond O, and C. So this is our reaction here. This is our reaction, and we are reacting this molecule with the hydrogen gas, HH, and we are producing. What we are producing here is CH here, and we have C, then O, H, and H here, and we have double single bond here, and C, H, H, H. So if we do this reaction, if we mix this molecule and with this molecule, 1 mole of that one and 1 mole of that one in coffee cup calorimeter, and we just allowed them to react, right? So how much heat they would give out? So how much delta H would be? So you could calculate the delta H by mc(T2 minus T1) if you remember your experimental thermodynamics. It's exactly like that, yeah? So if you have mixed this molecule with this molecule, let's say 1 mole of those, 1 mole and 1 mole of those, and you form this one, and in the coffee cup calorimeter it becomes hot, and then you calculated the heat using this equation, how much heat you would get. This Q is sometimes also called delta H because we are doing the reaction in open system, right? So that one. So everything is given here. So this bond energy, if you look the next page, like in the slide number 12, CH bond energy is given. CH bond energy is given. So maybe I can write here. Enthalpy reaction here. If you look the reaction there, the bond energy here, here is a H here, and here is also H, H, H. So there is a box. In that box there is a 436. Right here is a 436, meaning that this H and this H forming the bond, and in that case 436 joule of energy is being released or is being absorbed, right? If you are breaking H and H bond, you are supplying 436 kilojoule of energy. If you are making the bond, minus 436 kilojoule of energy is being released. So this is one thing. And let's look another one. If you look there, another one there is a O double bond O. Look all the way down there. O double bond O is given as 498. So if you look the last line of that slide number 12, O double bond O energy is given as like this. O double bond O energy is given as 498 kilojoule. Yeah. So O double bond O, and then H and H is given here. Now CH. Now look the CH. So CH would be 346. So C is here, H is here. So go like this one, down this one. Right here is a CH is how much is that? No, CH, no, HC. Where is the H? H is the first line. Where is the C? C is in the first 413. So H is here. So you look the H and C here. This is 436, and look the H and C. So if the bond comes between H and C, just like the multiplication table, and this is 413. So this is H, this is H and C. So if H forms a bond with the C, that's a 413. Make sense? So look that table, yeah? And then there is a OH. Let's look CO. Where is the CO? C and O. So if we look the C and O, that's a 358. CO bond is 358. Look the table, and CO bond is 358. C. That's a C, and here is a O, and come from C and look here, that's a 358. 358. CO bond is 358, right? Just look like that. And then another one here is what else? We have OH. Now look the OH. Look the line O, and look H, O and H in the first line. That's a 463. So H is here, O is here, and it's 430 OH. 463. OH is H and O is 463. So you can just look those table and you can find the bond energy like that. Now let's calculate how many bonds are broken and how many bonds are formed. First, let's calculate the bonds broken. So bonds broken. So how many bonds are broken here? Always this side is a bond broken, this side is a bond formed, right? This side, the right side is formation, left side is broken, right? You see here, so where is the change? This part here and this part here is same, so we don't have to worry about this part. Yeah, exactly same thing. And look here, this part and this part is exactly same. No worry about this one. Yeah, because those bones didn't form, so we don't know what happened there, but exactly they look like the same. But we have this one, but this one is not this side, so we break this, definitely we break this bone. And here is a C double bond O, here is a C single bond O, C single bond O. Definitely this is broken here, and this is formed here. So let's calculate the bond broken. Yeah, CO. So energy for the bone broken is CO. What is the C double bond O? So C double bond O, if you look there, C double bond O is a 745. Go to the slide number 12. The third line from the right, there's a 745. So to break this bond, we need 745. 745 kilojoule of energy. Yeah, 745 kilojoule of energy. And then this is also broken. H and H bond is broken. That is 436. 436. So add these two numbers and you'll get 1181. 1181 kilojoule per mole. It's all in 1 mole. So we are talking about 6.023 10 to the power 23 molecules. Yeah. Now these are the bond broken, and that much is the heat change while breaking the bond. Now bonds form. Now go to the bonds form and calculate the heat bonds formed. FORMED bonds formed. Formation is always this way. So where is the bond formed? This CO bond is formed here because there was a double bond here. Now here is a single bond. So that bond is formed there. So CO bond is, what is the CO bond here? We have 358. C is here, O is here, 358. So that's 358. And then which bond is formed? Now we didn't have a bond here. If you look here, see here there was no bond here, right? There was no bond here, but we have a bond here. So we got a bond here. So we form a CH bond here. So what is the CH bond? CH bond value is, this is S, this is CH bond value is 413. 413. Now, which bond we form? We have OH here. We didn't have OH here, right? So we have OH here now. So we have OH here. So we form that bond. So how much is the OH bond? So OH bond is this one. So this is H, this is O. 463. 463. So that is, yeah. So that is 1234. So if you add those, 1234 kilojoule. We are talking about 1 mole again. We are talking about not one molecule, not one atom, not one molecule of hydrogen, not one molecule of this one. We are talking about 6.023 10 to the power 23 molecule of this one, and 6.023 10 to the power 23 molecule of this one, and 6.023 10 to the power 23 molecules of this one. Yeah. So now let's talk about the total heat change. So enthalpy, that is enthalpy of the reaction. So what is the enthalpy of the reaction? That is delta S. Now we are going to subtract from the formation to broken. So this is a formation, all bond formed energy. So energy change bond formed minus energy change in bond broken. BOND bond broken. So like this. So bond broken are this one. Bond formed are this one. So 1234. So that is the bonds. Sorry, it's a bond broken minus bond formed. So bond broken minus bond formed. FORMED bond formed. So how much is the bond broken? That is 1181. And how much is the bond formed energy? That is 1234. 1234. And then this gives you how much value it gives is a minus 53 kilojoule per mole. Kilojoule per mole. We just write the kilojoule because we are all the time we are talking about the in 1 mole term. So this much energy is total change. So without doing any reaction, did we do the reaction using coffee cup calorimeter? We didn't do the reaction, right? But what we know is we know all these bond value, and we can easily calculate how much heat would release when we react this molecule with this molecule. If we mix 1 mole of this one and 1 mole of this one and react it, and how much heat would it release? You see that without doing any reaction, without doing any coffee cup calorimeter thing, we could easily calculate how much heat would it release by reacting this one and this one. It's just like how much heat it would release by reacting magnesium with water in lab number 11. We just use other data and we predicted, oh, this much is the heat, this much heat would it release by this reaction. Did I make it clear? Good. So already, so like this one. Now this is the negative. Is it an exothermic or endothermic reaction? See, without doing any reaction, we can easily tell that this is an exothermic reaction. What does the exothermic reaction mean? It works as a fuel. So if you mix together, then it gives more energy. It releases more energy than it absorbs energy. Yeah. So it's a kind of the exothermic reaction. -50. Good. So, okay, here. So there are other couple of example I put here. So let's look at the slide number 13. So slide number 13, we have one reaction. We are reacting H2 and we are reacting H2 and Cl2. Again, 1 mole. We are not talking about 1 molecule of hydrogen. We are talking about 6.023 10 to the power 23 molecule of hydrogen and 6.023 10 to the power 23 molecule of chlorine. We mix together, and when we mix together, they give a gas, hydrogen chloride gas. And again, we are talking about 1 mole here. Yeah. So we balance. We need to balance it. It's balanced now. Now look how much is the heat change? So we don't have to do this reaction to find out whether this is exothermic, whether it is endothermic, how much heat energy it releases, or how much heat energy it absorbs. We don't have to do anything. We don't need any coffee cup calorimeter, right? We just do we just look the bond energy and we can calculate that one. So this is the H2. H2 means HH. So HH bond. How much is the HH bond value? 436. So that's a 436 kilojoule per mole. And how much is the Cl? This is the Cl bond. Cl bond we are breaking. So how much is the energy needed for 6.023 10 to the power 23 molecule of Cl2 we should break? So that is 242. So you can look that up table and you can put those numbers there. Now look H and Cl. What is the amount of the energy for H and Cl? So for H and Cl, if you look the H and Cl in that table, that's 432. 432. Look the table there. That's H is here and Cl is here, and come through the H and go down. Here is a below Cl, and across H there is a 432 value. 432 value. So that is 432 here. So, but in the balanced reaction, how many HCl we formed here? 2, right? So we have to multiply by 2 by this one, like this. Yeah. So this becomes, so here is only 1 bond, here is only 1 bond, but there are 2 bonds because there is 2. So if you multiply those, this gives you 864 kilojoule, right? Kilojoule per mole. So we are just not talking about 1 molecule or 1 atom or something like that. We are talking about 6.023 10 to the power 23 of this one, and this one. Now what is the heat change? Heat change or enthalpy change? Enthalpy change. So heat change or enthalpy change, whatever you want to call, heat change is equals to, so broken minus formed. Our formula is broken minus formed. Add this one and this one. So that is 436 plus 242. That's broken minus formed 864. So if you calculate this one, you give minus 190 kilojoule per mole again. Yes, kilojoule per mole. So you see, without doing any reaction, just by looking at the data, we could tell, oh, if I get hydrogen and chlorine in coffee cup calorimeter, how much heat it will give to me? That much, 190 kilojoule per mole. Is it an exothermic reaction or endothermic reaction? See, without having thermometer, without doing any reaction, we could tell that, okay, the reaction vessel will be warm, right? It works as a fuel. Make sense? We don't have to do any reaction. So with just the available data, we can say, oh, if I mix, what would happen? It will become cold or it will become hot. Would it work as a fuel or it would work as a, we need to supply fuel to happen this reaction. Yeah? So this is also exothermic reaction. It works as a fuel. Good. Now, do I have other? So I think I am done with this this chapter now. So we start the chapter 9. Yeah. So chapter 9 is very easy. So I already put two lecture slide in Canvas, so you can just read those and should be fine. So this is our last chapter. So we talk a lot about the bond. So I just told you, okay, we have a bond, H bond, we have an HCl bond, we have a CH4 bond like this, CH4 bond like this. Exactly, CH4 is not like this, it is like this. So C is here, H is like this, H is like this, and the one H is going away from this board, and one H is coming toward you. So I showed you this kind of picture in the last class. So we have a lot of this kind of the bond here. So the scientists think that, oh, how is it possible these bonds are formed? So this chapter explain about this, yeah? How these bonds are formed? What is the basis to make, what is the base in which basis they form this kind of the bond? So in this chapter we talk about this, yeah? So we have two theory. One is a valence bond theory. So one we have is a valence bond theory. So how does the bond form? So that is explained by one is a valence bond theory. One is a valence bond theory, and there is a another one is a molecular orbital theory. Molecular orbital theory. Orbital theory. So which theory is better? Can we use both, or can we use one? It's very hard to tell. Some of the molecular structure are so well explained by valence bond theory, and we don't need molecular theory, molecular orbital theory. And some of the molecule cannot be explained by valence bond theory, and we need a molecular orbital bond theory, molecular orbital theory. So we use both theory so that we can explain most of the molecule that we encounter in daily life. Yeah. So some of the valence bond theory has some of the merits and some demerits, and molecular orbital theory comes there and try to remove some of the demerits of the valence bond theory and try to explain better. But molecular theory is also not complete, and it cannot explain all the properties of the molecules. Yeah, so we try to use both theory to explain the bonding in the molecules. Right? So let's look here. So what is the valence bond theory? So you already know about the orbitals. So I told you in the 7th chapter, s orbital look like this, right? This is a s orbital, it's fair, s orbital. And I told you p orbital looks like this, 3. So this is a py, another p orbital looks like this, pz, another orbital p orbital looks like this one. If you remember the previous class in the chapter 7, so we have one s orbital and 3 p orbital, and we have 5 d orbitals. 5 d orbitals. In this class, we don't talk about the d orbitals, so we are just working with these 4 kind of orbitals. And I told you, inner orbital don't take part in reaction. For example, let's say we have a electronic configuration like this: 1s, 2s, 2p, something like this. And which is the inner? So 1s is inner, right? Inner cell. So like this. So this is a neutron proton is here. This is a first cell. This is a second cell. So this is the second cell here. This is the first cell. So we don't work with this one. We only work with the valence cell. Make sense? Yeah. Good. So inner, we don't work in the inner cell. We only talk about the outer cell orbital or electron. So let's talk about this one. We have electronic configuration like this: 1s2, 2s2, 2p6, 2p6, 3s2, 3p3. So do we talk about 1s? No, we don't talk about this one. Do we talk about this one? No, we don't talk about this one. Do we talk about this one? Yes, because this is the valence cell, 3s3, third cell. We talk about the third cell in the discussion. Make sense? So we don't care about the inner cell. We only care about the outermost orbit, the valence cell. Yeah. Good. So let's look here. Bonds formed when orbitals on atom overlap. So what happens here is, let's look here. So this is a hydrogen atom. This is also hydrogen atom. So what is hydrogen atom means? This is the orbital of hydrogen. So there is a a neutron proton in center, there is a neutron proton center, and there is an outer space, and we give this is a 1s orbital. The name is 1s orbital, right? So what happens is, so the 1s orbital have how many electrons? 1 electron. So 1s orbital in hydrogen has one electron. So if you look the electronic configuration of hydrogen, that is 1s1, right? 1s1. So S means spherical. This 1 means 1 electron and 1 electron like this. Make sense? So what we do is we bring this atom together. So bring these two atoms together like this. So bring this way and bring this way and overlap these two. So what happens here is like this. So they overlap. How is the structure? So let's make it like this. So they overlap like this here. In this region, they overlap. So they come like, one come like this, one come like this, and they just overlap. It makes sense? So they just attach and they try to overlap each other. Yeah? So overlap each other, and those two electrons sit here in that overlapping position. They sit here. Those electrons sit here, and they form the bond. Make sense? So how does the hydrogen atom forms this bond? So this hydrogen atom has 1s orbital, that is spherical. This hydrogen atom has 1s orbital, that is also spherical. This has 1 electron, this has also 1 electron. Now these two orbitals come together and overlap, and when they overlap, in that overlapping point, these two electrons sit in such a way that they form the bond. So one may be pointing upward and another may be pointing downward, right? Because in the same place, they cannot sit exactly the same spin. So, and if they form like this kind of the overlap, we call the sigma bond. This is a sigma bond. This is sigma bond. So if one orbital is this and another orbital like this, and they are just overlapping like that, and they are electron occupying this position, and this kind of bond, scientists call this a sigma bond. Yeah. So like the head-on collision. So one car is coming this way, another car is going this way, and this to just smash each other in the head, right? So that is kind of the sigma bond, head-on collision. Good. Then I still have some time, so we just finished this slide number 2. Now let's talk about the slide number 3. I already told you the bonding involves the valence electron. We are not concerned about the inner electron, core electron, right? Now that's this, and half-filled atomic orbital on bonding atom overlap to form the bonds. You see that? So this is half-filled or full-filled? Half-filled, right? S orbital can have 2 electrons, but it has only 1, and it's also half-filled, only 1. So this half-filled orbital can overlap and form the bond. Make sense? If they were fully filled, they would not take in the reaction. Like that 2p2, 2px2, something like that, they would not take bond. Or 1s2, or maybe 2s2, maybe 3s2. If something is fully filled, they don't form the bond. Only half-filled orbital overlap to form the bonds. Bonds are localized between atoms. You see, this is localized, meaning that they sit in the same place, localized. These electrons are not moving everywhere. These two electrons are not moving everywhere. When the bond is formed, they are localized, just like you are localized. You are just sitting one place, right? When they just sit in that place, in that bond, they don't move other region like this. Make sense? So, and then this theory enables prediction of the molecule shape. We will talk about that one later. Now here is one example of fluorine. So I am drawing one example of fluorine here. Let's look at fluorine. So if you look the electronic configuration of fluorine, fluorine is number 9. So this is 1s2, 2s2, 2p5, right? This is a fluorine. So if you remember the chapter 7, so this looks like this. Now we are not interested about this 1s2. We are only interested about 2s2 and 2p5. Make sense? Yeah? Good. Now I'm not interested in the fully filled. 2s2 is fully filled here, right? S2 is a fully filled. So I'm not interested in this one also. I'm only interested in this one. So how does this look like? Let's look. So P has 3 orbital like this. P has Px, Py, and Pz, and I have 5 electrons. So I put 2 here, and 1 here, according to the Hund's rule. So I would put 1, 1, 1 first like this, and then I would pair to make this. If you remember this one from the seventh chapter, make sense? So like this. So this is one F. So I'm not interested in. You see here, this is fully filled. This is also fully filled. So I'm not interested in this one. I'm not interested in this one. I'm only interested in this one because this is half filled. Make sense? So orbital should be half filled. So maybe you can say let's say this is PZ, this is PX, sorry PY, and this is PX. So let's say this is a PX. Yeah, just for our make the discussion easy. Let's say PX is easy because we are so used to look the x-axis easily. So PX. Now this is one PX. So how does the PX look like? So I have two F. One F is here, another F is here. So I need to bring these two together and make a bond. So how does the F orbital of this PX orbital of F look like? Because I am looking to half fill. I'm not interested in the fully fill, right? Now let's write the PX orbital of this fluorine. So PX orbital looks like this. This is the PX orbital of the one fluorine. Make sense? And how many electron it has? One electron. One electron here. You see, one electron. I don't take this fully filled, right? Now again, another atom also looks like exactly same. So this is another fluorine. So this is another fluorine atom. Exactly one fluorine and another fluorine, exactly same. So I will put one electron like this here. This is also PX. Now what happens? What should we do to form the bond? So we need to bring those two orbital together and smash head on head. Yeah. So let's bring these two. So push this together, and it would look like this. It would look like this. So you push them together, and then this head penetrate this head, and this head penetrate this head, and those two electrons of this one and this one just sit here like this. Two electrons here. Two electrons here like that. So that's what this is a one fluorine atom. This is another fluorine atom. They form the bond there. Make sense? And this is also coming from the head-on-head collision or overlap, and this is called the sigma bond. This is also sigma bond. Make sense? So the picture in the book you might see a little bit different, but it is the same thing. How I draw here and how they draw here is the same thing. Don't get confused. So they are drawing this like this. So they are drawing like this one. So how do they draw it? Oh, they say they are drawing like this, and they may be showing this overlap region like this. They may be showing like this, right? So this is this one, this is this one, and this region is this overlap region here. Yeah. So don't get confused. It's the same thing. Make sense? Good. So this is more easier to understand. So when they overlap head on head, and they form the sigma bond. And where are those other electrons that I showed you? So let's say F and F. I just showed you head on overlap. So here was this one was a P, this was one a P, and I told you there are two electrons here. So this forms the bond. So that's a sigma bond. So if in normal we just draw like this, right? So but there are, if you look those other electron in the if you look the electronic configuration, that is 1s2, 2s2, 2p5, right? So electronic configuration of the fluorine is this one, right? So where are the other electrons? So I am not interested in this one. So 2s2. So you can put this 2s2 here, another 2s2 here, like this one. Now I'm done with that one. Now let's talk about the 2p5. So 2p5. I have three boxes here. So 1, 1, 1. So 2, 2. This is 5. Now I'm going to put this one as a. This is this one. I'm done here, and this one is this one. I'm done here, and then this one electron go here like this. Make sense? Yes. Good. And then exactly same here. So this one is 2s2, and this one is this one, and this one is this one, and one electron, this one, go here to make this bond because there are two electrons here. So this is those one electron coming from here, one electron coming from here. Did I make it clear? It's like that, yeah? Good. So this one is true. It's totally not taking part in bonding. Good. So still we have some time. Now, if you look the slide number 4, this is not really that important for us, but the people who do research in this theoretical chemistry, so they always show this kind of diagram. So I just want to talk a little bit. So how does this bond form? So let's say this is the energy. So then in this y-axis, this is energy, potential energy. So how does the energy change when the bond is formed? Let's say two hydrogen atoms are here. So this is one hydrogen atom, this is one hydrogen atom. We have two hydrogen atoms. They have too much energy. They are free and they have too much energy. Make sense? This is free. They are not making any bond and they have too much energy. Now so if you make the energy diagram like this, so this is far, right? So they have a lot of energy here. This is one point. And then now bring these two a little together. So this was here. So in this place, let these two atoms bring together a little together. See that I bring these two a little together, and this energy start to decrease. So energy here was high, energy here is small, right? Now bring these two more together. So more together like this. Now the energy becomes smaller like this. So like if two person are far away from each other, they have too much energy like this, very high energy. Now when these two person come nearer, a little nearer, their energy become, the system energy become a little less. Yeah. And then if you further go there, then come near, the energy become even less, and come here, still come near, energy becomes smaller and smaller and smaller and smaller and smaller. Make sense? So you are two people here, you are far away from each other. So she has more energy, so you have more energy. If you measure the energy of both, you have this system has too much energy. Now start to come close together, the energy of the system becomes smaller and smaller and smaller. Yeah. Why the energy becomes smaller? Because as the two people come together, they start to lose their energy to the out. Make sense? Good. So if I'm alone, I have too much energy. Now I'm married and I'm living with my wife, and she has so she has some energy, and we start to kind of make some kind of adjustment so that we lose our energy. Make sense? It's just like that. So when they start to pair, as they start to get come together, they start to lose energy, and their energy goes down, and at a certain point they become the lowest energy, and that is the bond energy. Make sense? So at this point, these two hydrogen atoms just touch each other and form the bond. That's the lowest amount of the energy. Now what happens if I push too much to these two guys together after bond formation? Now I start to push this one together, then the energy start to go up like this. Make sense? So this is the bond energy of the hydrogen. This is 436 kilojoule of energy that hydrogen has, is the amount of the energy of the bond energy. So when H and S bond forms, so they release 436 kilojoule of energy. We are talking about 6.023 10 to the power 23 molecule of hydrogen. Kilojoule per mole means. Yeah? Make sense? So the hydrogen atom were too far, so they have a lot of energy. And then we started to bring them together, so they started to lose some lose energy. And at a certain point, when they just touch each other and form the bond, and they lose 436 kilojoule of energy to be stable. Yeah. Now, if you further push this hydrogen atom more together, they start to repel, and their energy start to become higher, and the bond start to break again. Make sense? So if you come here, very stable. Now if you put more, if you push to more, the energy of the system start to go up, and molecules start to break because they start to repel each other. Make sense? So it's like this. So, but this is not really important in our class. So why I give the minus sign? Because when I were bringing the two hydrogen atoms together, they were releasing the energy. When they release the energy, that's the exothermic process, so we give the negative energy. Good. Now, so meaning that as we bring two atoms or two orbitals together to overlap, we lose energy to the environment. That's exothermic process. Yeah? Good. Now, good. So that's what I am talking there. Now let's go to the slide number 5. So let's talk about the slide number 5. So I just told you, if one orbital is like this and another orbital come here from another atom and they overlap here and they form the bond here, this is called sigma bond, head to head overlap, right? This is called sigma bond. Now this is like this, fluorine, and they overlap head to head. So there was a fluorine atom here. This is a 2px orbital of the fluorine. This is a fluorine atom. This is 2px orbital of another fluorine atom. This guy has one electron. This guy has one electron in outermost orbit. That's unpaired. So they come together and they pair the electron here and they form the bond there, and this is called the sigma bond, right? Now there is another kind of bond. We call that is a pi bond. So let's look here. So if you so that's I was just talking about the px orbital, right? Now we may have the py orbital here. This is a py orbital of fluorine. This is also it's not about the fluorine, some other thing. So maybe there is one atom. Let's say this is a carbon. This is a carbon. So we have a carbon atom at the center. Carbon here. So this is a py orbital of carbon. So this is py orbital of carbon. And then this one also py orbital of carbon, right? Yeah, they are pointing in the y direction, right? Now let's say we have one electron here, one electron here. Now you can bring these two together. Yeah, bring these two together like this. So these two carbon atoms come together and start to overlap like this. You see that? Now this is carbon. This is one py orbital of one carbon. This is a py orbital of another carbon, right? Now you see how do they rise head to head? No, they didn't collide head to head. They collide side by side, like one car. If it is just like this, let's say this is one car. Let's say this is one car here, and then this is another car here. And if this car hit this by head to head, that would be sigma bond. But another car comes here like this, and then they just push each other like this. They collide sidewise. Make sense? And that is called the side-wise overlap. So they overlap here, like this region. They overlap here, and those two electrons occupy this region, either this or this. So this is called pi bond. So this is one kind of the bond, and this is called pi bond. So side-wise overlap, and that bond is called pi bond. Make sense? So imagine that two cars come together in head collision and make a bond. That's a sigma bond. And two cars come there, and then they just push side by side, and they form the bond, and that is a pi bond. Yeah, good. Now, so that's like this. Now, I think so. It's an internuclear axis. So it's like this. So it's a. So let's say this is a sigma bond. So this is a carbon here. I have a carbon here. I have a carbon here. Sigma bond is just in the internuclear axis, right? But a pi bond is either from here or here, down. Yeah. So pi bond is either above the sigma bond like this, here or here. Make sense? So pi bond is either above or below the internuclear axis, but the sigma bond is just between the two nucleus. Yeah, it's just like that. So this is a sigma bond. If I have to make a pi bond, I cannot put here. I cannot put a pi bond here. I should put here or here. Yeah? So it's like that. Good. So I think we learned something here. So this chapter is pretty easy. So it will be fast. All right. So I'm going to stop this one. Thank you, everyone. So I'm getting the email. How are we going to take the exam? So the final exam will be online too. Yeah. So I think that's May 11. So